Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistor or physics perspective. This is lecture number 29 and the topic of the lecture is basically PN heterojunction diode. So, this is now we have already done a homojunction where you have taken both silicon on both the sides and the band gap is exactly the same. This is possibly the first time when you are actually looking at an application of a heterojunction in form of a diode, where you have two different band gap material being sandwiched together to form a PN heterojunction diode. Now, let me see what we will be doing in this lecture, the outline of this lecture. We will be looking at a PN junction or a PN heterojunction diode. So, these are all silicon, but then we will assume that either the heterojunction is a staggered heterojunction or it is non-staggered heterojunction and so on and so forth. And then look at the Fermi level position and how, if you add the two PN side together, how will the current flow in presence of bias and without bias. So, the first part which we will do is that we will look into the basic equation of a PN junction. Then we looked into the PN junction in forward bias. Before that we look into equilibrium, then in forward bias, and within the forward bias we will look into minority carrier concentration and its movement and what is the total current in forward bias. And then finally we will end up with majority carrier concentration and charge neutrality, and then the same heterostructure in reverse bias we will have a look at the functionality. So, if you remember properly, let me revise to you the basic PN homojunction where you did not have the band gap differences. There if you look very carefully, then you will see that there was a majority current carrier. In the reverse bias it was otherwise a minority current carrier, because for majority it would have been a hill, but for minority is actually a downward hill, right. And therefore, when you do, say for example, I will just draw your basic sort of a devices 101 sort of approach, where if you take a diode, and this is a homojunction diode, I have a P and I have an N here, and I do a reverse bias. So, I put a negative and I put a positive one. Then what happens is the depletion thickness will obviously be larger, right. But if you look at the energy band diagram, then the energy band diagram, since it is you are giving a positive charge here, therefore, energy band diagram which was initially like this will actually go like this. So, there will be a larger sort of barrier for the majority current carriers to move from N side to P side. But as you are aware that any N side or even P side, be it homo or heterojunction, will always have a minority current carrier because of thermionic emission. Because at T equals to 300 Kelvin, let us suppose, you are having some electron hole pair generation, right. Now, since here electrons are majority current carriers and holes are minority, then if you add EHPs, the percentage increase in the minority will be much larger as compared to the percentage increase in the majority. So, just to revisit and explain to you. So, if you look at the percentage change in minority is much larger, right, as compared to the percentage change in majority. The very fact that minority is very small in number, that is the reason this statement holds good, and that happens even in a heterojunction when you are actually fabricating a heterojunction. So, that is the reason I say that minority carrier concentration and the current because of minority carrier concentration has to be studied at some point of time. So, let us consider junction in which we have a P type semiconductor and an N type semiconductor. So, this is P type doped semiconductor is, let us assume it to be named as SC1, and N type semiconductor is doped as SC2. So, you can see that typically if you look at the band gap of semiconductor 1 is much larger as compared to that of semiconductor 2, right. And therefore, chi 2, which is the electron affinity for electrons, is much larger as compared to chi 1, because it is staggered. So, what I am doing is that it is totally overlapping. The P type semiconductor is fully overlapping over the N type semiconductor in this case, right. Though you do not look at this Fermi level at this stage, this is Fermi level 1 and Fermi level 2, just do not worry about these two statements at this stage, just look at the band gap and we will go one by one as we move ahead. As I discussed with you, the two semiconductor need not be necessarily the same, right? They will be different in nature in terms of, because it's basically a heterostructure. Therefore, I can have a p doped semiconductor which is made up of say some 3,5 material, and n type doped semiconductor made of some other material, such that the band gaps are different in this case. In this case, I will, as I told you just now, that Eg1 will be greater than Eg2, right, Eg2, which effectively means that Ec2 is lower than Ec1. So, Ec1 is obviously larger as compared to Ec2, and that is the reason Chi2 is much larger as compared to Chi1, which means that in the n type material, the energy required to make electrons go from the lowest conduction band to the vacuum level is relatively much higher as compared to that of the p type, right. That is what we have shown to you in this diagram in a sense. Now, let us come to a heterostructure. That means the previous diagram, if you look, we were actually, they were separated out and there was no heterostructure, or there was no metallurgical junction between the two. Now, what we do, we take them together and then we add them together, and quite interestingly, what will happen is that there will be a abrupt junctions being formed at the valence band edge and the conduction band edge, these abrupt junctions, and the height of the abrupt junction will be nothing but the difference in Ec1 minus Ec2. So, if I want to find this height, let us suppose this is delta 2 I say, and delta 2, and this is, let us suppose delta v, and this is, let us delta c. Then delta c will be referred to as Ec1 minus Ec2, and delta v will be referred to as Ev2 minus Ev1. So, the difference in the conduction band edge will be there. This is for that case, specific case, when the p type material or this n type material is fully embedded in the p type material in terms of their energy band diagrams, right. So, therefore, electrons can flow from a region of higher concentration where this one is there, and they can easily jump onto the second one, right, which is a n type material. They can easily jump from here very easily, right. They will, for it will be a more of a downhill, and holes will flow where you have a lower Fermi level to side of higher Fermi level, and that is the reason you see the holes movement from the valence band edge from the material Sc2 to Sc1, right. So, it's basically when you add those two together, in order to make the Fermi level equitable, I can say that electrons will flow from a region of higher concentration to a region of lower concentration, and they will try to make the Fermi level balance out with respect to each other. Now, please keep in mind that while doing so, I have not changed the value of the electron affinity or the band gap. They are always constant depending upon the type of material which you have chosen. This, when you add them together in a sort of a metallurgical junction, you tend to have these electrons being flown. How long will they flow will depend upon how fast Fermi levels are getting aligned with respect to each other. Now, since they are flowing downhill and it is an abrupt junction, there will be a sort of a diffusive nature which will happen in this case, in case of a PN heterostructure. Now, if you take the PN heterostructure and do the PN junction here, so if you look at the right hand side, you have an n doped structure here, and this is my p doped structure, and as you can see, this part, which will be the depletion region up till this part to this part, will be devoid of any free charge carriers for the reasons we have already known earlier. There will be charge carriers, but they will be actually fixed charge carriers, and this is the depletion region which we call. So, from minus xp to 0 and from 0 to xn is basically my depletion region thickness which we get, and this is n type dope, this is p type dope. Now, of course, pp0 will be equals to Na, assuming 100% ionization is happening, all the acceptor ions will generate pp0. pp0 is hole on the p side, if when you are generating the number of holes is pp0, and np0 will be equals to Ni square by Na, and that is what I have shown here. Ni square is the intrinsic carrier concentration by Na, and these all assumptions are all based on first principle, assuming you have a 100% ionization. Therefore, we can write down this important point that Ef for heterostructure minus Ec2, Ec2 is which one? This one, Ef2 minus Ec2, which is this lag is kT ln of Nd by Nc2, right. So, the energy difference will be equals to this ln of Nd by Nc2. Similarly, if you do Ev minus Ef1, Ev minus Ef1, well, I have not drawn the Ev, Ev will be somewhere very close to it. Ev1 is this one, right, and Ef1 I have drawn it here, will be given as kT ln of Na by Nv2. Na is the acceptor ion concentration and Nv2 is the number of valence shells available to you. Now, as you can see, if I go on increasing the acceptor or the donor ion concentration, right, what will happen is that ln of this quantity will go on increasing, right, and as a result the difference between EF2 and EC2 will also go on increasing as you increase the value of Nm. Now, the thing written on the left and thing written on the right are perfectly antisymmetric with respect to each other, and therefore I get number of holes assuming 100% ionization to be equals to Ni2 whole square by Nd, where Ni2 is the intrinsic carrier concentration in the second material, which is Sc2. The built-in voltage is difference of the EF1 minus EF2 that we have already known, and it is given by this formula which you see here, right, and it is given by Eg2, the second band gap material, plus del Ev is this one, plus kT ln of NaNd by Nc2 Nv2, right. If you add these three, I will get built-in voltage, which means that the built-in voltage will be higher if the band gap of the second one is higher first. Second thing is if del Ev is larger, and third is if the doping concentrations are larger. In all the three cases the built-in will be larger, which means that more of energy will be required or more of potential will be required for the electrons to cross over from a region of higher concentration to region of lower concentration, basically a diffusive process. So, this gives you a PN heterostructure basic idea, right, and how a PN junction is formed in this case. Now, let us take up a PN junction heterostructure in equilibrium, and we are applying a depletion approximation. What is a depletion approximation? You can see it from the figure shown here, that I am assuming that all the charged particles which have donated, so it is 100% ionization, and all the particles have been participating in the formation of the depletion region. So, what you get is on the p side you get negative charge associated, and on the n side you get a positive charge, and that is the reason there is a depletion region. And the area under this which you will get, right, the area under this is rho x. Rho x is basically the charge density, right, charge density with respect to x, and this is positive on this side and negative on this side. If you add those two together, it should be equals to 0, because charge neutrality has always to be maintained. Let us, with this basic knowledge exactly the same as a PN junction diode, let us come to the equilibrium PN junction diagram, the energy band diagram. As is expected, you will actually get sort of a break in the EC and EV diagram. So, there will be an abrupt change in the value of EC EV, right, and this is known as the discontinuity in the energy band. Now, you see the Fermi level has aligned itself, because you have reached to an equilibrium and therefore, the Fermi level has aligned, and the Fermi level is closer to EC2 on the right hand side and it is closer to EV1 on the left hand side primarily, therefore, meaning this to be as P and this to be as N. So, please understand in this case now, if you go back to your previous slides, previous discussion, here also Q chi 2 was greater than Q chi 1, or basically chi 2 was greater than chi 1, and the reason was that your conduction band on the N side was actually fully engulfed within the P side, right. Now, here also if you look carefully, this is the vacuum level, right, vacuum level is also has actually changed, right, but the expression that Q chi 2 is always greater than Q chi 1 is always maintained. Now, this is Eg1, this is Eg2 which you get, and this is Eg1 which you get, which is the valence band to conduction band of one, and you get valence band and conduction band of the second one, right, and del Ec, right, and you get del Ev, right. If perfect symmetricity is maintained, these will be equal to each other, which means that the discontinuity on the conduction band edge and the discontinuity in the valence band edge will be almost equal to each other, right, and they will give you a proper heterojunction conduction band. Now, if you look very carefully at this particular point, you see you have sort of a triangular, I have a triangular this thing. So, for an electron to this becomes a hill, but for this you will have these intrinsic energy levels which are basically aligned, and these alignment will be there for all practical purposes, right. This alignment will be there, and there will be quantum confined if the dimensions are very small, and therefore electrons and holes will maintain discrete energy level in case of a p-n heterostructure diode in equilibrium. Now let us plot electric field with respect to x in a p-n junction heterostructure. Then you will see that this is quite interesting, and I want to point it out, that if you plot electric field always will be negative, because please understand that when you are homo or hetero does not matter, when you are doing a p and n and your depletion region is in this manner, this will be positive fixed charges and this will be negative fixed charges, right. And therefore the electric field in the forward direction across the material is this, but inside the device it is just opposite, from positive to negative, and that is the reason you see the electric field is actually negative here, fine. And the rate at which the electric field goes from a 0 value to a very high value at the interface of the two, this is the interface, right. This is the interface of the heterojunction interface, right. Here the value of E goes to max, the maximum electric field is available here. So, but you see, since the doping concentration is not the same on both the sides, I have a problem that the depletion widths are therefore not the same. Therefore, I will say that xn is not equals to xp for all purposes, at least from this graph. Now you understand there is a one problem with this graph, actually not a problem, but you need to find out where the problem is. The problem is that you see there is a discontinuity at x equals to 0 for the electric field. At x equals to 0 there is a discontinuity apparently of the electric field. This is the discontinuity of electric field, you see it is coming here and this is starting from here, right. So try to figure out why that electric field is there, and that is coming from this expression which you see from here. This is the Poisson equation which you can see, and then from here I get the electric field variation with respect to x to be equals to q n d xn minus x by epsilon 2 and epsilon Ex equals to minus q n a x plus xp by epsilon, right. And since xp is negative, I get a negative quantity in the output side, but electric field is xn minus x. So what you will get a negative electric field in this case also, right. So this is for x between 0 to xn, and this is for x is between minus xp to 0, and it quite interesting, obviously depends upon the doping concentration on the n side and p side. Let us come down to the electrostatic potential. In fact, it would be better if you study this one first and then electric field, but nonetheless electrostatic potential, if you find out, it will be nothing but dVx dx will be giving you the electric field. So we were able to derive this quantity from the potential variation. As you can understand, the potential variation will follow the line as I have shown to you, and it goes to V built in at the edge of your n type, and it almost goes to 0 around the p side, right, which means for an n side it will be a hill which will require to break up here. And if you charge per unit area, if you find out, it is q times nd times xn, q times Na into xp, which will total charge. If you maintain charge neutrality, this is to be correct. So this is charge neutrality which I am expecting, charge neutrality. Because of charge neutrality you will get this, and you will get a revised value of V built in as this much, and the value of xn and xp to be equals to this much. Interestingly, this xn, let us take, that is easier to understand. So if you look very carefully between these two equations, everything looks exactly the same, only thing is that this is Nd by Na and this is Na by Nd. Na is the acceptor ion concentration which you are putting for the p type material, and therefore and Nd is the donor type material, and just reciprocal of that is basically your xn. Now if you vary, therefore if Nd, and that is the reason, if Nd equals to Na, then this quantity will be equals to 1 and your xp will be exactly equals to xn, right. And that is the case when your doping concentration both on the n side and p side are exactly the same. In that case you will get the equal values of xn and xp, and the electric field will be also same in both the direction. Now let us do it in a forward bias. Forward bias means on the p type material I put a positive bias, and on n type material I put a negative bias, and we have the here the diffusion will exceed the drift for minority carrier injection, which I have written here if you look carefully. So the electrons will move now from this direction and the holes will be moving in this direction, as you can see, because of the delta Ec and delta Ev which is already present there. So in forward bias you will get a surge of electrons available to you, and therefore your currents will be relatively large in case of a forward bias, just like in a case of a ordinary homojunction silicon diode. These are the equations which are there. You don't have to go through it very in a detailed manner, but just for completeness sake I has written this statement. But what we are showing you here is the electron concentration, which is the minority carriers on the p side, and hole concentration, again a minority carrier on the n side, right. Now in this case, this is interesting statement which I have written here, that for the main bottleneck for current flow are the neutral regions or semi neutral regions and not the depletion region. In the, if you remember your PN junction, you had a strong depletion region which was not letting the current flow for the majority current carriers when you are inserting the voltage, right, and you need to cross the barrier. Here that is there, but the more important point is that those regions which are either neutral or quasi neutral, they tend to be the bottleneck for any forward biased current to flow in a PN junction heterostructure, and that is being shown here in this expression. I am again assuming that Xn and Xp might be equal or might not be equal in this case. Now let me come to minority carrier concentration during the forward bias. So this is N side. On the right hand side you have an N side, on the left hand side you have P side, right. On the N side, if you see, the minority carrier concentration is maximum at the edge of the depletion and starts to fall down almost exponentially as you move towards the edge of the N side, right. Why it cannot be found inside the depletion region or the quasi neutral region is because the strong electric field will throw them out either on the left or right. Same thing is happening with Nx. Nx is the minority carrier concentration for electrons on the p side, right. And as you can see, any excess electron which you inject on the p side will actually recombine with hole, right, and there will be, obviously because of the diffusion, there will be a diffusion current available to you, which will depend upon how my minority current carrier vary with respect to distance. So that is the reason you see, if this variation is very steep, it implies that del n del x, right, with respect to x is very large, implying that your diffusion currents will be also very large. And these are the two equations which you solve even in homojunction. You can solve it here also. So this is basically, if you look carefully, is on the left hand side you will see del n del t is equal to 0. What is del n del t? How my minority current carriers are varying with respect to time, and in this sense it does not matter, because the reason is it does not matter because anyway it is with respect to space and not with respect to time, and that is the reason they have been assumed it to be 0. Now if you take up the minority carrier concentration in forward bias, I get two lengths, and these lengths are diffusion lengths which are available to us and depends upon the diffusion constants and the carrier lifetimes here, right, and we can get the boundary conditions available here. Now I will leave as an example or to question to you why we are doing this, why we are putting a question mark here. I need you to understand this point very clearly, and you might respond it while you are studying it, that you need to solve this differential equation and you require a boundary condition. So boundary conditions will be fed by these two quantities. This tells me how many number of minority current carriers are there at minus xp, edge of the depletion, and that is given by np0 e to the power qv by kt. And if you look at the right hand side, number of holes, you will get ppn0 e to the power qv by kt, right, and therefore it is a function of voltage V, right, at the edge of the depletion. And when we say n of minus Wp is the width of the depletion, we define that to be as np0, because we in the under strong reverse bias condition V will be negative, and the e to the power minus V quantity will be almost very small. It will go down to a very low value, it will not contribute to overall value, and therefore you will be almost remaining equal to 1, and therefore you will be left with np0. So I will tell you what do I mean by that. When qv equals to kt, then e to the power 1 I want to get, which means that qv equals to kt. If I do, then I get e to the power 1. E to the power 1 will be, you know what will the value will be, that if you multiply with np0 will give you the exact value at forward bias condition at the edge of the depletion. Same thing for, and this is the expression for the variation of nx, which means the carriers with respect to x electrons, and this is for holes with respect to x, right. So just keep in mind how these variations are, and if this V is very large, I can afford to neglect minus 1 in this case, and we can carry forward with the understanding of Nx and Px in case of a minority carrier concentration. Now, so this is the last extension which we see, and we now try to show to you how the carrier densities will vary with respect to x, right, how carrier densities will vary with respect to x. And as you can see, since the carrier densities are related to carrier concentrations, therefore they follow almost the same profile as the carrier path, and they give you the results also here in the same manner, exactly like it. Looks complicated, but if you break it down mathematically, it's very easy to understand. Just the last point to keep you in contact with the forward bias. Now in the depletion region there is no obstacle to current flow, right, and therefore if we ignore the recombination in the depletion region, we will have the current density to be almost constant at the depletion region, which means that the current density will not either show an increase nor a decrease at the junction region. And the reason being that I ignore electron hole recombination, I get this profile into consideration, and I say that the total current within the depletion region will remain almost constant and is given by JEX plus JHX, where J is the electron concentration and JH is the hole concentration. Therefore, the total current flowing through the device, you do not have to worry from the derivation of this one. This is again for a heterostructure, heterojunction PN junction, the current is given by this formula. It depends upon therefore area of cross section. Higher the area of cross section, obviously larger current will be flowing through the device, and that is the reason it is shown as Q times A multiplied by this big quantity here. Now this is quite interesting, and based on this you can get large number of numerical problems, and I can get large number of solutions also from the numerical problems. Let us come to the majority carrier concentration and charge neutrality. Now the majority concentration on the P side, the change in the majority carrier will be Px minus Na. Na is assuming 100% ionization, Na is the acceptor ion concentration. So Px minus Na will be the increase in holes on the P side, and similarly increase of electrons on the N side will be given an Nx minus Nd, right. And if you look at on the right hand side, this will be also known as Nx minus Np0. Nx minus Np0 is the number of electrons on the P side, and Nx is the electron concentration. So this is my Nx, and if your Np0 is somewhere here, then the difference between these two is basically Np0 at this point. So this is basically again x dependent quantity which you see. So this is Np0. The difference between Nx and Np0 is this small decrement which you see here, right, and that will give you the value of. Same thing happens for the P type, and therefore excess carrier density of majority must balance the minority carrier density. Therefore the P side total current minus electron current, and on the N side total current minus the hole current for majority current contribution in forward bias. Let us finally come to the reverse bias. As you can understand, in reverse bias this side will be pulled further down because of application of a positive bias on the N side, and I get two types of condition, Xn and Xp. The two depletion thickness on the N side and P side have been known to us, and that depends upon the value of V built in and the applied voltage Vb, right. And as you can see here also, it is Nd by Na, this is Na by Nd which you see. So with this, let me recapitulate what we did for this lecture. We looked into a heterostructure band diagram, right. We looked into heterostructure band diagram, hetero band diagram, and we looked into the fact that there will be discontinuity in the energy band. This discontinuity in the energy band is primarily because of the difference in the band gap between the two material. We looked into heterojunction PN junction diode in both forward bias and reverse bias. In both forward and reverse, we looked into majority carriers and minority carriers. This also we looked into majority and minority, and we explained to you that how does the current get influenced heterostructure based PN junction diode. With this we finish this lecture. Thank you.